Okay.
In this lesson, we shall focus on this module, MAM 2000W 2LA linear algebra. We shall look at past exam questions today, but most importantly, would have a perfect opportunity to look at the June 2024 paper. Right, so, and we've gathered a lot of the questions. Right, I've gathered all the questions and I can see the code might be like MAM 2011F, whatever. Maybe the codes change, I know. Okay, right. So this is the module. Now, I want us to look at the question you asked. Okay, there's a question you wanted us to look at, and then obviously, now write A, where A is this matrix here, as a product of an elementary matrix and an upper triangular matrix. You see that? And so if you look at this very carefully, you are able to see that to do this question, we always take the matrix A and do the following. Right, we take the matrix A, and after having taken the matrix A, we perform row reduction on it. Right, so the matrix A is 1, 0, minus 3, and is 3, minus 2, minus 3, and is 0, 0, minus 2. Look at the fact that this particular matrix question, they always ask the same thing, but it is obviously based on just one equation on these elementary matrices. And now you see the sign issue is resolved, okay? Because now you're like they're getting negatives and getting positives, whatever, right? So now, given this matrix, you need to write A as a product of an elementary matrix and an upper triangular matrix. So what do we do? What we do is we take this matrix and we row reduce it to the final result they want, upper triangular matrix. So we want to make it upper triangular. Right, so upper triangular, we just need to make sure that this entry here becomes a 0. And therefore,
Yes.
the first row, it's going to be okay. Then we have the second row minus 3
I have three.
times the first row. And that is going to give us a 0 here. It's
0
going to give us minus 2 there. And it's going to give
and
us 9
6.
minus 3, which is a 6. Well done. And this becomes 0, 0, minus 2.
But
Let's see. Okay.
yeah.
Now, looking at this carefully, the couple of things that now we have, therefore, this matrix here is what? Is an upper triangular matrix. Right?
Yes.
It's an upper, so we have the desired result. But then what do we do now at this point? What do we do now at this point? So what we do right now at this point is we then realize what we've done. So, which means that we'll define an elementary matrix 1. But first, we would define or consider and the identity matrix of 3 by 3 right size. And then now it's 0, 1, 0, and then 0, 0, 1, like this. We perform, we try to get the elementary matrix through row reduction. And now at this point, realize that this is the operation we applied. Right, so we said row 2 minus 3, row 1. And with that, that means that we'd have 1, 0, 0, and then we'd have minus 3, 1, 0, and this is
Yeah.
0, 0, 1. Okay, so this is what we're going to have here. And this is the elementary matrix. Now, this one is an elementary matrix, but it's not what they want. Okay, and this is the trick. So now, but we need to go through these first and then say, we are able to see, therefore, that we then say thus. Right, we need to say thus. Thus, there is an elementary matrix, so we call it E1, which is this one here. 1, 0, 0, minus 3, 1, 0, 0, 0, 1. Okay, this is the elementary matrix that we need to get first. But it's not what they want. Because why is it that it's not what they want, this one? It's not what they want because by definition, let's look at the definition in the study guide. And I wanted us today, and I'm sorry for today because we had a power reduction issue in the morning, and with no power, and the power just came back later in the day. I don't know what was happening. Okay, right. But now, if you look, then the what then happens by definition is you always write the final result. So you always write the upper triangular matrix becomes the elementary matrix times the original matrix. So this is the equation they always ask. So you always say, it doesn't matter what they are saying right, it says that. But you need to say, what is the original matrix? It's A.
A.
And you perform row operation on it. And now, if it's the matrix A, you performed an elementary row operation on it, it means that you multiplied it by an elementary matrix, you multiply the original, and you get a new matrix. But now, then the examiner now is coming. Then from this equation, then you can come here and then say, right, A is a product of an elementary matrix and an upper triangular matrix. So which means that now you need to solve for A. Right, so yeah, to solve for A right now, what then do you do? Right, so to solve for A, you're able to see that what you ought to do, I'm going to write it in like some 2 steps here. Right, so what you need to do, you realize that you have U is equal to E1A, and you need to solve for A. So this implies that you're going to have E1 inverse U is equal to A. Is equal to A, like so. Right, and this is exactly what they want. Because now we've written A as a product of an element. So this is going to be the elementary matrix they want, but it becomes the inverse of the matrix we got. Right, and so now A is written as a product of an elementary matrix together with an upper triangular matrix. And look at this. Then it means, therefore, A is E1 inverse U. Okay, now we need to get the inverse of E1, but now we know that E1 is what? Right, elementary matrix 1, it's this one here. Okay, it's exactly this one here. It's 1, 0, 0 minus 3, 1, 0, 0, 0, 1. Right, so it is 1, 0, 0 minus 3, 1, 0, 0, 0, 1. Is it the correct one? Yes, 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 yes. Now, this is the matrix E1, and then you need to find its inverse because that's what we need to put here. Right, so obviously then you then say it's 1, 0, 0 minus 3, 1, 0, 0, 0, 1. And then we have 1, 0, 0, 0, 1, 0, 0, 0, 1. So you augment it with I3 here. Okay, and now you perform the row reduction. So now to get the inverse, we need to make sure that here we have the identity, and it's very easy, just one row operation, meaning we're going to say row 2 plus 3, row 1, which means you have 1, 0, 0, 1, 0, 0. And now you then say for row 2 is row 2 plus 3 times row 1. So that gives us a 0 here, a 1, a 0, a 3, a 1, 0, yes, all these kinds of stuff here, okay? And then it means we then can say hence the elementary matrix E, which is the one they want, is this one here, which is the inverse. It's 1, 0, 0, 3, 1, 0, 0, 0, 1. Okay, so now they want the things. So we need to, yeah, this is the elementary matrix they want. And we have the upper triangular matrix we've already got. The upper triangular matrix we've already got is this one here. And then it is 1, 0 minus 3. Right, so it's 1, 0 minus 3. Okay, and then it is what? 0 minus 2, 6. 0 minus 2, 6, right? And then it is 0, 0 minus 2. 0, 0 minus 2, like this. Okay, so this is what we then have. But now you need to look at this and say, okay, because they said right A is a part of that. So it means, therefore, at this point, what then do we have according to this? According to this, A is E1 inverse U. Right, so you know that A is E1 inverse U, which means that, therefore, A is the E1 inverse is this one, which is 1, 0, 0, 3, 1, 0, 0, 0, 1. And then what is the U? 1, 0 minus 3, 0 minus 2, 6, 0, 0 minus 2. Okay, so this becomes A. A is this product. We need to check if this is true, of course. Is this correct? So in other words, if you multiply these two matrices, do we actually get A? If we claim that A is 1, 0, 0, 3, 1, 0, 0, 0, 1, multiplied by 1, 0, minus 3, 0, minus 2, 6, 0, 0, minus 2, like so. And now we do row by column multiplication. This by that is going to be 1. This by that is going to be 0. This by that is going to be minus 3. This by that is going to be exactly what? 3. This by that is going to be what? It's going to be exactly a minus 2. Yeah. This by that is going to be exactly what? Okay, this is going to be minus 9. Right, it's going to be minus plus 6. And that is minus 3. Right, and this by that is going to be a 0. This by that is going to be another 0. And this by that it's minus 2.
Minus 2.
So, yeah, this confirms that indeed this is correct.
Okay.
But what is the secret to getting the matrices in the exam for this course? Okay, they always play one trick. What is the trick? The trick they use is they want you to get an elementary matrix, but the elementary matrix is just the inverse. It's the inverse. It becomes the inverse of the first elementary matrix you get. Because what did you do? We had the matrix A, which is 1, 0, minus 3, etc. And then now, they then said you need to write A as a product of an elementary matrix and an upper triangular matrix. So obviously now we just need to transform A to an upper triangular matrix, and it takes just one elementary row operation to do that. And after having done that, then we realize that we already have the upper triangular matrix, meaning simultaneously we can get the corresponding elementary matrix. But this is not the one they want. Why? Because the elementary matrix we got, E1, has been obtained from A. Because it was obtained from A, it means that it is E1 times A that produces the upper triangular matrix. So because it is obtained from A, then we must form this equation. Why is this equation necessary? Because from this equation, then we can answer the question and say, now write A as a product. So we must solve for A in this equation. And immediately when we solve for A, if U equals E1A, we need to solve for A. How do we solve for A? So to solve for A, we then say, we take the inverses both sides, etc., etc. Okay, right. But now it becomes then, because in principle, I need to make sure this is clear enough. In principle, if in mathematics you have UE1A, right, to get the value to solve for A in this equation, what we do algebraically, we multiply the left by E1 inverse, but we must also multiply the right by E1 inverse, and we still have the A then. And this then means that you have E1 inverse U is equal to A, like this. So because of this, then it means the inverse must be on the right side also. You know, for example, I mean, the E inverse cannot be, on the right of the U. You know, it is like on the same side of the equation. Okay, so yeah, I just wanted to give a comment on this kind of a question, and I realized that obviously, yeah, it becomes so popular. Yeah.
Can you also explain? Let's say U was equals to E2 E1A. Is it like that, or is it E1 E2A? No, I want to know.
Okay. Yeah.
Is it
yeah.
E2 first or it's E1 first?
All right. That's
if we have
So now,
more than one elementary matrix.
Yeah, we have more than one elementary matrix. Yeah. So now,
yeah, please write it down.
Yeah. Okay. For example, yeah, I
so
get
I can
the point.
see.
Yes. Right. So for example, right. So now you are saying that if you have a series of elementary row operations. Okay.
Yeah.
If you have a series of elementary row operations, that is obviously part of. I want to I'll just give you a reference just now. Just in a split second, I'll just give you a reference now because I want us to speak about the facts. I'm gonna just in a split second, just give me 1 second, there's an equation. I'm gonna cite the page number of the study guide because it's exactly when I looked at the study guide that they are actually asking this in connection with what is part of the study guide. Okay, so I want to just write the equation that they cite in the study guide. Just give me a split second. I'm just going through the study guide, but very quickly here. And I'm going to write down exactly the kind of equation that it's going to work.
Okay.
Right. So in just a split second, okay, yeah. Right. Okay, I'll be with you now. Yes, okay. Now the study guide has 292 pages, but never mind that. I want to write an equation here and then cite the page number. Okay, right. So it has 292 pages, and I want to write the equation that is central to what you're talking about right now. Okay, so that it really can make a lot of sense because I wrote one equation because yeah, sometimes it really can be a series of those equations. I'm going to just mention that now because it's very important, the question you're discussing, because tomorrow they might bring a question like that where you have like, you know, 2 or 3 of the elementary matrices, and then you'll be like, okay, but what do you then do? And this is what I want to actually discuss just now in a split second, right, in a split second. Okay, I'll just discuss it right now in a split second. Okay, all right, please allow me that, right. Please allow me that, right. Okay, right, I'm with you. I'm trying to retrieve that. I want to cite the page number. Yeah, elementary matrices start from page 59. Okay, they start from page 59 of the study guide. And now, if you look at it, definition. Okay, right. This definition I want to mention, 1.6.7, which appears on page 62 of the study guide. Okay, what is this particular definition here? It is then saying that, I'm going to write it here. If you obtain, I'm going to try to be much faster. Right, if you obtain a matrix B from a matrix A by performing, right, by performing elementary row operations, elementary row operations on A, okay, right, then A is said to be, right, it's said to be row equivalent, right, row equivalent, said to be row equivalent to B. More precisely, A is row equivalent to B if there are elementary operations. Elementary operations, E1, E2, E3, and so on, up to EK, such that, okay, I'm going to write, I want us to discuss that, such that B is equal to EK, and then you have E2, E1, so you write them in this order, and then A. Okay, so this is what you actually obviously write it as. Right, but most importantly, according to Lerma, right? So according to Lerma 1.6.10, and this lemma appears on page 63. Right, there's a lemma there, and what is this lemma? This lemma is saying the matrix B is equal to EK times E2, E1 times A. Right. So now, obviously, these elementary operations can be paraphrased to elementary matrices, meaning you work the first one that multiplies A, it's the first elementary operation. The next elementary operation is put after that, sort of away from A, and you put them away like that. And with this, then, this is equal to B. So it's not equal to A. But you see, in the exam, they then say, write A as a product of an elementary matrix. So if they say write A, what is A going to be? So A is going to be the B with the inverses. So, for example, what will A be the same as? Right, so you are able to see that if you solve for A here, what are you going to have? First, you're going to have B here, and then you're going to have EK inverse. Right, so you're going to have, for instance, B. If you solve for A, you're going to have B. And then because the EK is so much on the, so now you're going to multiply on the left by EK inverse, so that you're going to have EK inverse. Then after that, you're going to have EK minus 1, if you like. EK minus 1 inverse, and so on. So that now you have this inverses, and there until you have the last one. And then it becomes E1 inverse, for example. Okay, so this is what you're going to have if you have a series of these things. But you see, it's not good to memorize this. As much as they ask this, but it's easy to say, what is the first row operation on A? That is elementary matrix 1, E1. And then what is the next elementary operation? Is E2. But how do you then multiply them? You know, so the way you multiply them is that you always put the first one closest to A, then the next away from A, like that. If that makes sense. Okay, yeah, and obviously, I mean, there's one question we can do that is like this now. Okay, it is here. I can try to reach that question. Right. Let me try to reach the question very quickly. There's a question like this that we're going to do right now. I want to show the question so that you're able to, okay, I'm running through because I've put a lot of these questions, but now I'm running through the things, and there's a question that is going to have, is having the two of them, you know? He's having two of, yeah, he's having two of these, just so that we can discuss. Okay, and then, yeah, let's see this one. Yeah, it's this one, for example. There's a part of elementary matrices that A and that. Let me see. Okay, here, for instance, let A be this, right? A is a part of elementary matrices. Okay. It's not exactly what I want. Let me see. Okay, there's another one. I'm trying to find. Okay, let me see. Okay, this is eigenspaces, eigenvalues. Let us see this one. It's not exactly what I want. Let me see. It might be this one, I think. Okay. Okay, there's one that is like several elementary matrices. So you have that one. Let me see. Okay, let me see. Let's see if I can have that. Okay, there are tons because I've put a lot of them. I'm trying to reach one question that is exactly of that form here. Okay, exactly of that form. Let me see. Okay. Right. Okay, let me see if okay, we look at this, but now I want to see if I can find yeah, this one. Yes, this one. Okay, find elementary matrices U1 and U2 and a matrix U in row echelon form such that this is the case. Something like this. Okay, so this is the kind of thing you're talking about, I'm sure.
Yeah.
Okay, right, where you have like several elementary matrices. Okay, right. I want us to look at these and obviously just use that theorem and that lemma. All right. For example, what would we do here? But first, we start with the matrix A. Okay, that is the first thing we do. So now we write this matrix A like this, and then 0, 0, 2. And then now we then say if we have this matrix A, then we need to find elementary matrices E1, E2, and now, we don't think about this first in the beginning, but we look at the final objective. U in row echelon form. So we just need to write U in row echelon form, right? So now to write U in row echelon form, then it means that we would have to perform the elementary operations on A, right? So obviously, if that is the case, we're going to realize that the first row is okay. We need a 0 here. Right. And to get a 0 there, what do we do? I know it is this question. Right. What do we do? We then can just say, if you have this one is row 2, we then say minus 1/3 row 1. Because if you divide this by, if you multiply this by 1/3, right? So it's row 2 minus 1/3 row 1. And that is going to give us what? 0, 0, 1. And then this one is going to be 0, 0, 2. Okay. And then, obviously, now, you see, that is why there must be 2, these matrices. Why must they be 2? Because now this one is not in row echelon form. In row echelon form, we need actually a single pivot. Okay, we need a single pivot, and therefore would need to perform further because of the fact that this is a multiple of that. This row is a multiple of that. So now you then say we need a 0 row here, which means you have row 3 minus 2, row 2. Row 3 minus 2, row 2. Right, which means that we have 0, 0, 0, 0, 0, 1, 6, 0, 0. Okay, so this matrix will then be in row echelon form. So, but now obviously there are a couple of things, but the 0 row then is at the bottom. And because of this, then it means that there are 2 elementary matrices. Now we're going to start with I3, for example. 1, 0, 0, just the ordinary one, and then we make it an elementary matrix. And then now we're going to actually apply the first one here. And then we're going to call this one E1. Okay, what is this E1? Then we're going to apply this one because we said row 2 minus 1/3 row 1, right? And then now if you do that here, it means the first row is okay. So it's 1, 0, 0. And then row 2 is row 2 minus 1/3 row 1, which is minus 1/3, 1, 0, 0, 0, 1. Okay, so this is what we have. This is what we have. Row 2 minus 1/3 row 1. This is what we have. So now this is going to give us elementary matrix 1. Okay. And then now, but it was not enough, obviously, for us to reach the row echelon form of the U, because this one here is the U they want. But now, the U, there are 2 U's you can get, but yeah, this is 1 U you can get. Okay. Now, in this case, you then need to then say what is E2, right? So you need another identity matrix, 0, 1, 0, 0, 0, 1. And then now you then continue to perform the operation, the elementary row operation according to the second stage. Okay, let's check. This is the second stage, right? So what did we do in the second stage? We said row 3 minus 2 row 2. 1 0 0, right? 0 1 0. Row 3 minus 2 row 2, which is 0 minus 2 1. You agree? Like that. Okay, so this is exactly now, this one is called elementary matrix 2. But then what is the equation that we're talking about? Unfortunately, once again, it's not exactly this. It's not this exactly. This one is the one of the inverses. Okay, so because these things have been applied, it means that you're gonna say the original matrix A times the elementary matrix 1, elementary matrix 2, it's gonna give us exactly the upper triangular matrix we want. So this is actually what these things have, because we start with A and then we perform an elementary row operation on A, meaning we multiply by E1, and then we do the same. And then we get an upper triangular matrix. So then the question is, now we come to this. Now we come to this. What is this? Then obviously now you start this E2, right? So you have U. This E2 will come first because it's at the end here. And then you'd have E1, and then equals A. So this is exactly the thing now. This is exactly what you get. So you see, it's a bit tricky. So this actually, therefore, would be the answer to this. Let us continue to realize this. So now, if you look at the fact that you have E1, so these things are mixed up a little bit because there's E1, there's E1, so you can give them different names. But now you got E1, but you need E1 inverse, right? So, but now you look at the fact that you got E1, and then you'd have to get its inverse, right? So, and what is E1 itself? It's this one, which is 1 0 0 minus 1/3 1 0. So it is actually 1 0 0, and then it is minus 1/3 1 0 minus 1/3 1 0, and it is 0 0 1. It is 0 0 1. Okay, now we need the inverse of this. So let's augment it with 1 0 0 minus 1/3 1 0 0 0 1, which means therefore you'd have 1 0 0 0 1 0 0 0 1. And now what then we need actually the inverse of this, so we need a zero here. So we're then gonna say row 2 plus 1/3 row 1. Right, which is 1 0 0. The first one is okay. And then now the row 2 plus 1/3 row 1, 0 1 0. Okay. And then it is 1/3 1 0 0 0 1 0 0 1, like this. So, and this one, it's the actual matrix they want. So it is sort of the E1 inverse, which is 1 0 0 1/3 1 0 0 0 1. Okay, but it's not everything we need, because we need to get also the inverse of the E2. So you take this E2, which is this one. What is the E2? It is 1 0 0 0 1 0. Yeah, this is 1 0 0 0 1 0. Right, so we have the E2 1 0 0 0 1 0. Let me check. 1 0 0 0 1 0 0 minus 2 1. Right, and then we have 0 minus 2 1. Okay, this is exactly the matrix we have. So what you then do here is you take this one, 0 0 0 1 0 0 minus 2 1, and then you have this here, 0 1 0 0 0 1. So you can write it at the bottom. This right at the bottom. Right, writing it at the bottom, we obtain the following. Okay, we'll have this. So now with this, then you're able to see that what we have, we need the identity here. So to get the identity, we can just say row 3 plus 2 row 2, right? Which is 0, 0, 1. And then we come here, right? And if you come here, it becomes 0, 2, 1. And then 0, 1, 0, 0, 1, 0, 1, 0, 0, 1, 0, 0. Okay, so with this then, this is the inverse. So which means therefore that E2 inverse is this one, which is what we want, 1, 0, 0, 0, 1, 0, 0, 2, 1. Okay, we're going to test these answers anyway. We're going to test them, you know, if this thing is going to make sense in the equation that we need to get. So now you need to then remember something, that in this case, the A must be, A is equal to E1 inverse, E2 inverse, U. Right, so, which means that A is E1 inverse, E2 inverse, U. Okay, is this true or not? Is this true or false? And that is what we sort of need to establish here. Okay, is this true or not? So now we need to then come here and then say, if we claim that A must be E1 inverse, E2 inverse, U, what is the E1 inverse? Right, the E1 inverse is this one, 1, 0, 0, 1, 3rd, 1, 0. Okay, so it is 1, 0, 0, 1, 3rd, 1, 0, and what? And 0, 0, 1. Right, 0, 0, 1, like so. Okay, this is the E1 inverse. Let us look for the E2 inverse. E2 inverse is this one, which is 1, 0, 0, 0, 1, 0. 1, 0, 0, 0, 1, 0. And then it is
0,
what?
2, 1.
0, 2, 1. Thank you. Thank you so much. 0, 2, 1. Okay, so, and then now you put here the upper triangular matrix. What is the upper triangular matrix that we've got? Okay, we got it on the previous slide here. So the upper triangular matrix that we got became this one here. Okay, it became the 600, 001 with zeros. Okay, so it became the 600, 001 with zeros, like this. Okay, so now you need to check if this is true. Right, such that obviously, if you multiply all these things, you get A. Let us check. Right, we can multiply these two, and then we just leave this one first for a moment, and then we're gonna just perform the multiplication of this one. Right, if you multiply this with that, what you get? We first get a 1. This with that, we get a 0. This with that, we get a 0. This with that, we get a 1/3. This with that, we get a what? A 1. This with that, we get a 0. This with that, we get a 0. This with that, we get a 2. This with that, we get a 1. Then we continue with the multiplication process. We multiply this with that. Right, we get a 6. And then this with that, we get a 0. This with that, we get a 0. This with that, we get a 2. This with that, we get a 0. This with that, we get a 1. This with that, we get a 0. This with that, we get a 0. Okay, this with that, we get a 2. It's exactly the matrix A. So which means, therefore, this is correct. And therefore, we have found the elementary matrices. So it means that we can then say thus, the matrix E2 here is this one, 1, 0, 0, 1/3, 1, 0, 0, 0, 1. Okay, so that is what we're getting here. Okay, like so. And then now the matrix E1 is what? It's this one here. 100010021. We have the upper triangular 000000100 000 like this. Okay, right. So these are the matrices. Now, this paper, I think it's the one that was written in 20. Is a 2023 paper, if I'm not mistaken? 2022 paper.
Oh, I don't know. I think it's
Okay, yeah, okay, yeah, definitely. I think that this is a 2023 paper, the very first one we discussed. Okay,
yeah.
but now, this is exactly the paper that, but now, you need to take a look at these and obviously try to make sense of it. And, but now, we're just showing. So, what is the secret to getting these elementary matrices right in the exam? Okay, the secret to actually being in a position to solve these particular questions on elementary matrices, the secret lies in the fact that you need to um, know one equation. One equation. What is the equation you need to know? The equation
Okay.
that you need to know is to say that if you start with the matrix A, you perform the first elementary row operation, you get the first elementary matrix. The next elementary row operation produces the next elementary matrix. The third one, and then this one is going to produce the result B, or in this case, it would be the result U, for example. But then you need to know this is the equation that's very important. And then you can juggle around and then be able to, because now they will then say make A the subject. Here you just make A the subject. But if you make A the subject, you take them in the right order. You multiply them in the what? In the correct order. Right. What is your input on this one? Any suggestion? Any discussion you would like us to sort of obviously be in a position to have on this one? Right. Your
No.
take. All right. So
Yeah.
everything is pretty fine with this, right?
Yeah. No,
All
I
right.
understand. Thank you.
Okay, good. Right. I want us then to continue and look at the next set of questions. And right, the next set of questions, which is right, those questions, the question 4, for example, right? Right. So I'm moving quickly to question 4 right now, which is the one we're discussing. And we're going to take a look at that one and make sure that we're good with it. Right. So we're going to make sure that we're good with it. I'm just moving, I'm moving through the bulk of this. Right. I'm moving through the tons of the things here. And so as I cruise through, I'm cruising through tons of these because I've combined all these here, right? I've combined all these, I've combined all these, and I've combined all these, and I've combined all these. Right, moving. Okay, let's see what we have here. Right. We are moving. We are moving. We are moving. We are moving. All right, never mind, please. Yeah, just forgive me because yeah, I'm cruising through. It's tons of things here. I have organized nearly. This is it's a set of nearly 900 discussion slides. Okay, I'm going through. Okay, never mind.
Okay.
I tried to break this down. Yeah, I tried to break this down into so many. Okay, so I'm like repeat because yeah, this is the paper that we need to discuss today. Right, this is the paper that we need to discuss today. Okay, it's the paper that you sent. Okay, this one here. So you would like us to start. Okay, this is the paper you sent. So you would like
Yeah.
us to discuss, for example, like which question again, please? Okay, I can see this. Question 4. Okay, great. Let us move towards question 4 and see what we have. Right, so we're moving to question 4. Question 4. Let's see, question 4. Okay, this is exactly question 4.
Yeah.
Right. This is exactly question 4. Right. If you look at this particular question 4, what exactly do we get here? Let us move and solve these particular questions and solve these step by step. Okay, good. Question 4 says, let's solve it together. Right. The first question says that we have a story. Let V be an inner product space, right? Right. And A, a non-empty subset of V. Put A orthogonal sets, or A, there's something called the A complement, which is the orthogonal complement of A. So you need to put the orthogonal complement of A to be equal to V, vectors in V, vectors V, which are elements of the vector space, which is the inner product space, such that the inner product of V and U is 0 for every U in A. Okay, so this is once again what we call the orthogonal complement. How? How do we know? Because orthogonal means that the inner product is 0. Okay, so now something you need to remember there. Orthogonal means that the inner product is what? It's 0. Now,
0.
yeah, you need to then prove that, but it's 0 with the things that are in A. So the things in the V that is in the A perp. Okay, sometimes you can call these A perp, A perpendicular. Okay, so my lecturer could call that A perp, like A perpendicular. So A perpendicular is such that now if you take the product of a U in A and a V that is in A perp, the inner product is 0. And obviously, this is sort of in the orthogonal complement set, this V, right? So prove that the orthogonal complement of A is a subspace of V. Prove that the orthogonal complement of A is a what? Is a subspace of V. Okay, now I wanted to tell you something, the secret about this course. You don't need to learn a lot of the theorems.
Okay.
What theorems you need to know? Like for the subspace, you need to learn the subspace definition. Like for this one, to prove the subspace definition, what are the conditions? There are 3 conditions. Now, the first one is not empty. The second one is the addition. Close. And then close under addition. The last one is scalar multiplication, you know? Yes. Then you are done. So now, this is the secret for this course. So for these questions like question 4, you need to learn just a subspace, the definition, meaning first you must show that it's not empty. It contains a 0 vector. Next, it closed under addition. Next, it's closed under scalar multiplication. That's all. Okay, but obviously, how do you prove that it is not empty? Right, so obviously you need to note that, in other words, you need to observe that if you then say the 0 vector is here, you allow this V to be 0, and then you take the inner product of 0 with U, surely the inner product of 0 with U, it's going to just be 0, okay? So now you would then say, the first point, you need to say 0, the 0 vector is an element of A perpendicular. Why? Since, because this is what you need to prove. Right, so it's an element of A perpendicular since the inner product. You take the 0 vector with U, the inner product is equal to 0 for every U vector U in A. Right, so obviously here we're then saying, right, and with this, then you can come and then say, that's what did you say there? I can see that you are beginning to realize this. So this one is not empty.
It's not empty.
Yeah, it's not empty, you know, because it contains a 0 vector at least. Okay, so this is what you can say first. What is the next thing to prove? The next thing is to prove it's
addition.
addition, right?
Mm.
The next thing to prove is what? It's addition. So with addition, you need to take two elements and add them up and argue that their sum is there. So we can suppose W1, W2, which are like vectors, are members of this set. We take two elements out of this set. And then now these two elements, we must add them up, right? And then if we add them up, we argue that the result is there. Right, I can see that your lecturer even made the things very complicated. Right, but now the easiest thing is to say, you suppose that W1, W2 are in the what? In W perp. Then you take the inner product of the sum. You just add them up like this. Right? So now the things that are first, because in this inner product, you have V in V. The V's are in W perp, and then the U are in what? In A. Right. So you take the inner product with a U. With a U, like this. Okay? That is what you do. You take the inner product with a U. And then if you take the inner product, you use the property of the inner product. Okay, you must learn. Okay, this is the property you need to learn. Right. The property of the inner product you need to learn now. This means that you have W1U plus
and
W2. Okay, you learn that it spreads like this. You know, right? So this is the thing, and I can see that they've set that in the length of the vector. But now, because if this is the case, you need to know that the W1, W2 are in W perp, but the U, which is in the second component, becomes an element of what? Of A. So you need to say that this U is an element of what? Of A. So that here you then say, this one is in W perpendicular and the U is in A. So these are like orthogonal vectors, and the dot products. Okay, obviously this is a much general space inner product, right? So it's 0 plus 0. 0 plus 0 becomes what? Becomes 0. And because of that, thus we then say the sum. That's the sum, which means W1, W2 are elements of what? Is an element of what? It's an element of W perp. Then what is the next point? Also, what is your question here? Do you have a question here?
No, I understand.
No question. Okay, good. So we move to the next point. The next point. So now, as I said, for this course, there's no theorem quite you need to learn. Just the definitions. You just need to know the definitions, and then you sort it, and you just get to your distinction there. Now, what do you say? Here you need two things, because you need to prove scalar multiplication. So to prove scalar multiplication, you need a vector and a scalar, right? So now you need to say suppose. So you take a vector that is here. What will the vector be? You can call it W or anything else. You can even call it V. Right. So you call it W perp. So you take a W that is in A perp. And you take lambda. That is what? That is a scalar. Okay, these things are normally on the real numbers. Right. So you take this one to be a real number. So, and this real number is a what? This real number A is it's an element of R, but it's an element of R, a scalar. It's an element of R, a scalar, so that. Now, you then say, you take, so now you multiply these things. You multiply these things here. So you need to then say lambda W, like this, right? And then you take U, like you form this one comes from A perp, and then you take with the U, right? And then if you do this with the U, what then do you get out of this? Okay, this is a property of the inner product. The scalars can be taken out, you know. So this scalar goes out, and this is the property of the, okay, this is a vector. And then now you have a W that is in A perpendicular, in the orthogonal complement of A, and the U is in A. Okay, these are perpendicular, are orthogonal vectors, and their inner product is is 0, so that we have that is the case. And because of this, then you can proceed to then say what? Hence, right, lambda W becomes an element of what? Becomes an element of A perp. A perpendicular. Okay, my lecturer used to call it A pep. Okay, now, and immediately when they said like A pep, you know it's A perpendicular. It's like containing the perpendicular elements, those elements that are like perpendicular to the elements in A. So yeah, so but this is exactly so. What have we done here? We have done 3 things for the subspace. The first step, if they say prove it's a subspace, what are you supposed to do? The first step is to say, in particular, if they say prove is subspace, it means that 0 is an element of that set already. So you can start by saying 0 is an element of the 0 vector is an element of that set. The set you want to prove is subspace is what? Is A perp. It's the orthogonal complement of A. So you then say the 0 vector is an element of what? Of the orthogonal complement of A. You say that, then you provide your justification here, but I can see that your lecturer did not even provide a justification on why this 0 vector is there. Your lecturer just wrote that this 0 vector is an element of A perp, of the orthogonal complement of A. But it is necessary to say it is an element of A perp, since you need to justify that to show that you understand, you know why. Because many times some lecturers, when they are marking your script, it might not be one person who's marking the script, you know, because the students are many at university. And then now some of the lecturers will be like, if you say, you know, the 0 vector is an element of the orthogonal complement of A, they will just ask why. You get the point. There are lecturers who just ask, write on your script there. They will say why. And then they take marks because of that. They're like, okay, yeah, they take marks. So you're not going to get the 5 that you need to get. Okay, so now my point is, then you need to first say 0 is an element of A perp. If you need to prove that is obviously the case, 0 is there. And you then say since. Then you can substitute the 0 into the condition. The condition is that you must take the inner product of these two. Then substitute here, because now the 0 is in A perp. A perp things are the V's here. The V's appear in the first argument. And the second argument, then you have what? You have the members of A. And therefore the result becomes 0. For every U in what? In A. Thus A perp is not empty. Is not empty. Then the next point is to then say, if you take 2 members of A perp, 2 vectors from A perp, then you need to show that their sum is there. So you add them up and then you put into the inner product. And then now you use the property of the inner product, because sometimes they ask you, I have seen that in the test, they asked you to even do the lengths, you know. And then now in the lengths there, they ask you the U plus W, U minus W. Okay, they ask you something like this. Okay, now this is the same thing. You do it component wise. Okay, let us do this one. If they would give you U plus W, how would you spread this one? Right, so I'm just teasing you. Maybe I can give you a chance, because I'm just giving this to just check your understanding, because I've seen they asked it somewhere, you know, because sometimes they ask the length, ask for the length, but they asked these things. Now this one requires you to just remember the property of the inner product, but also the property of the inner product, the complex inner product space, because this one is the real. There's something called the complex. Okay, I'm gonna get back to that, so please do not forget it. Okay, the complex inner product space. What would the complex inner product space be? So the complex inner product space would say, if you have U, okay, let's call it V, or case, right? Because it just is standard. Okay, the first one, it's a V. Then if you have lambda U, then this lambda, if you take it out, and this lambda is a scalar, if you take it out, then it becomes like this. Okay, you might have not done this property yet, but now if this lambda is coming from the second argument, it develops, it attracts a complex conjugate. It attracts a complex conjugate if it comes from the second argument, but it's when you're dealing with complex vector spaces. Okay, but obviously, I can see that in your school, I think it's mostly the real, the real things. But
They only
complex, yeah, it's
focus
all
on
real
real.
numbers. Yes, but now there are complex vector spaces, and now the complex vector spaces would say the inner products themselves are inner products that involve like complex numbers. So if this lambda is to be a complex number, then it cannot, because like here, we pulled it out of the first argument, and then it was just lambda. But if you pull it out of the second argument, it becomes lambda bar, the complex conjugate. But obviously, if it is real, if lambda is a real number, then the complex conjugate of a real number is just the number. Because these complex conjugates, they work on complex numbers. They change complex numbers, but they do not change what? They do not change real numbers. Any question on this one? Okay, yeah, I wanted to mention something. I wanted to test your understanding on this one. Okay, it just crossed my mind because I saw you. There's a question I saw that they brought, because sometimes they ask for the length, like if they say, what is the length of this vector? Right. And then now if you have u plus w and then u minus w, how will this be expanded? What's the expansion of this? Have you thought about it? I'm just teasing you because I saw it in this exam.
Yeah. That's what I wanted us to this question.
Okay, that's fine. Right, but now there are a couple of things. There are two ways to do these. But first things first, you look at you treat this one as one vector, or you treat this one as one vector. Okay, if treating the second component as one vector, then it would mean that you'd expand it as u minus w plus w, u minus w, like this. Okay, so if you treat this as one vector, then you expand. So it becomes the same as u plus w, u. Okay, because u plus w, u, it's the same as u plus w, u. Yes, something like that. Okay, yeah, I'm just showing how, because you need to know the properties of the inner product, because sometimes if you give these to a student who has not learned the properties, they might do wrong expansions here. Okay, so this is the thing. So this is not, it's not necessarily the dot product. It's not necessarily the dot product, because a student can just say they are multiplying things. There's no multiplication. Okay, so you'd have these, for example. So you treat this as one vector and then allow these to expand with to interact with u, but also to interact with what? With w. And then, yeah, after that, then now you treat this one is already one vector. So now you expand into this. So that's going to be u, and then it's going to be plus u minus w. Okay, the minus can go out here.
Yeah.
Okay. Now you come to this one. Now the w, u minus w, you write w, u, and then you can write plus, you can put a minus and that. But this minus now can go out. Okay, so in which case you can have the minus there. But I'm then saying then you can use that, because sometimes they can set a tricky question and say that, these are orthogonal. They are orthogonal. If they are orthogonal, then you might need to say these ones that are different are going to be 0. These ones are different are going to be 0. Okay, but the vector cannot be orthogonal to itself. Okay, a vector cannot be orthogonal to itself. So u cannot necessarily be 0, because it's the vector with itself. So a vector can't be orthogonal to itself. Okay, a vector cannot be perpendicular to itself. Doesn't make sense. Okay, all right. So that's something that. Any question on this one before we move on to the next point?
No.
No question. Okay, let's move to the next thing. Part B, for example. Right, we move to part B. Okay, here is part B. And part B says, let R3 have its usual inner product. Let R3 have its usual what? Inner product. That is the dot. Okay, this is very important. So now, here they're dealing with the dot product. Right, so if they're dealing with the dot product, this is the usual inner product. So that's very interesting. So they want to make things easy. Okay, so you have D equals this set. Now find the basis.
Hello.
Yes, please. Did you lose me there? Okay, right. Let R3 have its usual inner product, which is so you are dealing with a dot product here. And you have that D contains these two vectors. Find a basis for the subspace